So the first important theorem is the Pegman's upper bound theorem. So this basically says that if you want to sell a neutron on the secondary market, it'll cost you more than if you just did it directly with the reactor. When the state of the reactor is in the PEG state. Then we also show that in order to simplify the reflected calculations, we assume also that the net volume is less than some number, as well as the volume of the amount that you're actually converting to neutrons. So in this case, when we say like selling neutrons, we mean the combined action of doing either partial beta decay then fusion. In the case of buying neutrons, it's the fission and then the beta decay. So this is the opposite, the lower bound, which is if you want to buy a neutron in the secondary market, it'll be again cheaper to buy directly from the reactor instead. And because we do these like combined actions of fission, fusion, and then partial beta decay, fission, then beta decay, and then partial beta decay, and then fusion, we have this like effective fee, which sort of represents the fee you pay for those combined actions. Yeah, so the thing with there's a way that we can calculate like these effective fee. It's like there are some equation for it, but as we found out in this, as we were working on Gluon W, these end up being like really complicated, like a complicated polynomial. So then the effective fee you're trying to solve like the roots of this crazy polynomial. So it gets a bit unwieldy. And in the case of selling neutrons, since you're doing a partial beta decay, you also have to calculate how much of your neutrons are you going to convert to protons before you do fusion. So in the case of the theorems, because of the simplifications we made, we can obtain like some analytic equation, right, for this gamma factor. But generally you have to end up solving solve for the roots of the polynomial. So the third theorem is the peg robustness during market crash. So we can show that the price will still be the price you pay for the stablecoin will still be the local price during the PEG, which would be during the PEG state, even if there's a base coin price crash. And this tolerance is determined by this equation, R minus 1 over Q star divided by R. The next one is no insolvency. So the equity of the bank of the reactor is always positive. And this just follows from like the definitions of the protocols. So. And the fifth theorem is the monotonically increasing equity per reserve coin. So the equity per reserve coin, it means the proton price. So it always increases, or it's always increasing, assuming that the target price, the neutron target price from the oracle remains constant between actions, and that you don't convert neutrons to protons in the deep PEG state. And I'll go over that later as well. So I mentioned here that in the deep PEG state, the beta decay minus, so converting neutrons to protons. that we assumed was true, that the absolute value of the net volume was less than the base coins in the reserves. It's like intuitively, it really made sense. And so initially and it basically ends up as being false, okay? And this affected our beta decay phi equation. So before it was in this picture, it's like the minimum of these one or this linear function, this linear equation. Before it was just a linear equation. So because this lemma was false, then we could end up getting beta decay phis that were negative or like less than one or greater than one. So we had to change it to this new equation. Like it simply is a minimum of one in the linear equation. And it ended up being false because you show this trick that if you start with some amount of protons, divide by 2, then beta decay, do a beta plus decay with this amount to convert that half into neutrons, and you do that infinitely, then you can get a cumulative volume that's exceeds the reserve amount and the limit as you go to infinity. So yeah, so basically this means we just have to change our beta decay phi equation. Yeah, there's no bounded dilution because you can always make protons, so your share of the equity can always decrease. So so backgrounds are possible, but because of the beta decay phis, at a certain point, it becomes pointless to sell. So you can wait again until the volume of reactions over the period decreases, and the beta decay correspondingly will decrease. So this is an important theorem that unfortunately wasn't true, and so it's called the no reserve drainage or value preservation theorem. So basically, the concept is simple. It just means that ideally you would want the value of your total balance after a reaction to be less than or equal to the total value before. So as we were working on the proof, it ended up being false for beta decay plus in the depeg state, and this weird difference or this value called d showed up, and yeah, it just so happens that if this value is positive in the depeg state for beta decay plus, then this inequality didn't hold, and then similarly as well when it was negative when you're doing beta decay minus. Yeah, so as I mentioned, so what this would mean is that converting protons to neutrons in the depeg state when you're doing a beta decay plus can increase the price of protons. And then like the inverse happens for the beta decay minus. So why does this happen? It's because the fusion ratio equation, once based on how it was defined for Gluon W, once you depeg, it becomes a constant. So it's like the minimum of Q star, and it's either the minimum of Q star or PNT, like the oracle, the target price times the circulating supply of neutrons divided by the amount of reserves. So once you're depeg, it'll be Q star, and it's like a constant. So it doesn't matter what the reserve ratio is. So the way to fix that is, so you want to make it a linear, instead of a constant, you want to just make it a line, but not y equals x. You want it to be, so that's when the reserve ratio is 0, the normalized reserve ratio will be 1. And still haven't managed to prove it yet, but we think that this will make the value preservation theorem true in all cases, so when you're pegged and depegged as well. Yeah, so it basically, in fluency, like we would just fix that, the normalized reserve ratio and normalized fusion ratio when you're depegged. That's it for me.